This is an unusual science event for us because the audience has been studying this subject, right? This is really unusual where the entire audience is well aware of what we're talking about, and everybody here is a student of and a
there's
practitioner.
a seat in front, and I just tested negative, so you can be completely assured.
I tested negative yesterday as well. So Sid, you've written very eloquently and very powerfully and very influentially about COVID-19 in The New Yorker, in Cell, in your own venues, and I actually want to ask you more anecdotally, because this is something we're living through, in the same way that everyone has a 9/11 story. Where were you? What did it mean to you? How long before it diffused away? I want to ask you anecdotally what your experience personally has been of this time.
Well, there's been a medical experience, there's been a scientific experience, and there has been a personal experience. So it's best to divide them up in sort of three angles. Obviously,
because that's exceptional that you've had the medical experience and the scientific experience.
Right. So the medical experience, let's talk about that first. I mean, I'm a cancer physician. Cancer patients are particularly susceptible because they're immunocompromised. I don't want to say I was prescient about the plague, but I think it was in February or maybe in January, I went to a bar mitzvah. And Mark Lipsitch, the epidemiologist, who's written a lot about, the Harvard epidemiologist, who's written a lot about COVID, is a common friend. And someone came up to me, and there were no masks. We were in a synagogue somewhere.
It was February?
January, I would say January, yeah. And someone came up to me, a friend of mine came up to me and said, Mark Lipsitch says that it's going to be really, really bad. And I said, add 12 reallys to that. Because there was a sense, I think, within our community, because we had already started hearing about some of the words you don't want to hear, words like asymptomatic carrier. Those are
airborne. Airborne's not a good word.
You don't want to hear aerosol, airborne, asymptomatic carrier. You don't want to hear a word called R0 equals 2.3.
Right, which is the infection rate.
The infection rate. You don't want to hear a case fatality rate in some populations, of 1%. Those are words you don't want to hear. Right. And those words had already begun to appear in the press. And so I said, add about 10 more reallys to that. This is in January. So the medical experience of this was that, as you know, in New York, there was a time at Columbia, because we were up in Washington Heights. There was a time when the ICU beds were so full that the bone marrow transplantation units became. I'm a transplanter. I'm an oncologist. And as an oncologist, I know how to manage a crashing patient. This is part of what you learn as a transplant physician. And we pride ourselves in never sending patients to the ICU, because we run our own ICU. And so there was the experience of running an ICU outside the ICU, because we had patients all over. So that was the medical experience of COVID, and the fear and the constant surveillance that we had to do. This was a time before the tests were available. We were using clinical diagnosis. We were asking people, can you smell cheese? I mean, that was the level at which, that was.
So it's the timeline that kind of amazes me, because the CDC was well aware of COVID in December, right? Why weren't we told to wear masks? It's not like we haven't had past pandemics. I mean, March 15th, I was still planning the next day to try to fly to Costa Rica for a holiday, right? And I was going to take my daughter, and my 13-year-old had more sense than I did, where she was like, we're not going to Costa Rica, Mom. And that's March. So what happens between December and March that nobody's telling us to wear masks?
So, I mean, I'll give you a little bit of the timeline. Many people know the timeline. So, towards the end of January, the first patient, as far as we know, there probably is not patient zero. I don't believe in patient zeros, although I believe in the stories of patient zeros. A patient arrives from a 30-odd-hour flight from Wuhan into Snohomish County in Washington State, near Seattle, with signs of a pneumonia, and he's doing badly. So he gets hospitalized. And if you want to hear, if you want a minute-by-minute, day-by-day expose, I would strongly suggest you read the New Yorker piece that I wrote on that. It's called "What COVID Teaches Us About American Medicine." I'm not going to go through the whole piece now, so it's online. It's free. Then something very bad happened. Two or three things very, very bad happened, and we want to talk about them because we need to not have them happen again. The first thing that happened that was very, very bad was that people in Washington, at UW, one of the University of Washington, one of the preeminent universities in the world, have a pathology department, and it's run by a virologist named Alex Greninger, who I spoke with and have had long series of communications with. Greninger figured out that this was COVID, among other people. He was not the first person to figure it out. And he said, testing for a virus in the nasopharynx, oropharynx, is not so hard to do. Viruses have sequences, RNA, DNA, doesn't matter. In this case, it happens to be RNA. You can test for it. The trouble was that the CDC was also making kits to test for COVID. And they had started making those kits in January while they knew about the infection in Wuhan. But the problem was that the CDC kits didn't work. There was a missing component. The first batch worked, and then there was a batch problem. And we can talk about in the Q&A session what a batch problem means. But there was a batch problem. And so the CDC said, hold on, let's fix our kit before we give what's called an emergency use authorization for other testing kits. So 42 days passed.
That's a lot of days in
42
this
days
pandemic.
is an eternity for a virus where you can infect 3 people a day.
Right, that's the R naught factor you were
that's the
describing.
R naught, exactly. It's 42 days. I mean, this is an absurd calculation. In 42 days, if you multiply an R naught with 42 by the number 42, you'll cover the entire population of the Earth.
It's exponential.
It's an exponent, right? So you'll cover the entire population of Earth multiplied by many times. 42 days passed between the detection of the first case in, as I said, Snohomish County in Washington, before the CDC opened an authorization kit to test for COVID. That's mistake 1. Mistake 2 was that, and it continues to be the case, mistake 2 was we have a picture of a man wearing a mask behind us.
This is from the 1918, the plagues past.
Exactly.
The
we do, and
Spanish
we can
flu.
talk about it.
Yes, we should definitely talk about plagues past because it seems so insanely obscure.
Yeah.
And yet
But
here we are.
But in those 42 days, we knew that frontline healthcare workers, nurses, and long-term residents of nursing homes could be protected by N95 masks. And we knew that those masks very soon...
Those masks were made in China as well, which was hit
And so
by
that
COVID.
became, so there was a supply chain problem. And that supply chain problem amplified. So in fact, we now know that even simpler masks would have worked. But certainly N95s would have worked. And there was a supply chain problem because we had no supply chain anymore in the United States of N95 masks. Our emergency supply was depleted, and we didn't know how to decontaminate them.
Well, can we talk about simpler masks? Because I'm actually curious about this. So I have a simpler mask. I don't wear an
I do too.
N95 mask.
I have also some masks.
And I was at our local over here, San Pedro, little plug for San Pedro, at the end of the block, and they have this beautiful hand sanitizer, and I put the hand sanitizer on, and I could smell it with my mask on. And I thought, does that mean my mask is not working? Like the fact that I can smell the sanitizer, does that mean I'm not protected from the aerosols?
So I'm sorry, I promise I will not toot my horn, but there was an earlier article that came out before the second one, again in the New Yorker, where I said that for every respiratory virus that we know, there is a concept of a viral inoculum. In other words, whether you get infected by a virus or not, or a bacterium or not, is not a binary phenomenon. It depends on the amount of virus that you get infected by, and we can talk about that in great detail.
Yeah.
And as you remember, there's a famous theory, there's a famous Swiss cheese theory, right? So the Swiss cheese theory is that you can imagine every barrier to any event as a series of slices of Swiss cheese, right? So if all the holes in the Swiss cheese are perfectly aligned, then you can go right through. But if every piece of Swiss cheese has holes in it, in other words, every mechanism of protection, social distancing, masking, isolation, quarantine, and even medicines, vaccination, et cetera, each one is a barrier with a percentage attached to it of protection. That percentage is not 100%. There is no, and there's unlikely to be 100% protection for any and all of these things, hand sanitization. So what happens is that you get an infection when there is a straight line through the Swiss cheese. Masks are one part of that Swiss cheese, and no scientist has ever claimed, aside from these N95s, which are really highly protective, no scientist has ever claimed that they're 100% effective. But a 50% effective mask is better than a 0% effective nothing.
And if two people are wearing it, even
and
better.
if two people are wearing it, then you multiply that 50%, right?
So can I just redirect for a second, because I really want to ask you about the science of it.
Yeah.
And first of all, there are basic things like, what is a virus? Is it alive? And what does it want?
Right.
It's a very strange beast, a virus.
Yeah, so we can talk about viruses in general, and we can talk about coronaviruses
viruses
in particular.
in general are,
Right, so
because we know that
viruses
there's
in
a threat of a
general
lot of viruses.
are not alive by the conventional definition of life. They cannot independently reproduce themselves. They are typically a DNA or RNA, and they typically have a coat. And the coat is typically made of lipids or fats and proteins. And they can be a combination of them, or they can be one or the other. They infect cells, which are alive.
But that's the only way they can reproduce,
And then
is
they
symbiotically.
they parasitize or co-opt or acquire the capacity of the cell to reproduce, and they make copies of themselves. So they may need to make two kinds of copies, and that's important, or two kinds of molecules to make copies. They need to make a copy of their DNA or RNA, depending on what kind of virus it is, and they need to make some way of making the coat around the virus. And then they bud out of the cell. In doing so, they often kill the cell, and we can talk about why or how. And then they go on and infect. So one cell can produce 1,000 virus or virions, and then they go and produce more, and those go and produce more cells, and this process.
Super strange beast, because unlike bacteria, right, so a lot of the common misconception is, why don't we just give antibiotics? It's because it's not a bacteria.
That's right.
It's a virus, which is a different entity altogether, but bacteria are alive in the conventional sense. They
That's
reproduce.
right. So bacteria can reproduce independently, or they don't require the cell to reproduce. There's some minor exceptions to this, which live on the edges of the bacterial world. But that said, viruses are unique in the capacity that they don't have the capacity to reproduce by themselves. They rely or they parasitize the cell's apparatus to reproduce, and in doing so, they kill the cell or they incite an immune response that ultimately kills the cell.
I mean, isn't it a strange phenomenon that there is this thing called a virus which is not alive in the conventional sense? There are not that many examples of such a thing. And that
well, in fact,
even the word virulent
right.
is derivative of virus, but that they're so aggressive.
It's actually probably the other way around. Probably the word virulent came first, and the word virus came afterwards. But all of that said, in fact, viruses are extraordinarily common. Most of them don't infect humans.
Do we know how many viruses there are in the animal kingdom?
There are thousands. Most of them infect bacteria. A lot of them infect bacteria. They are bacterial viruses.
Right. The bacteria are very good at fighting viruses.
They're very good at fighting viruses. We can talk about that in a second. But they infect viruses, but a fraction of them infect humans.
So there's like, let's say, I mean, I've heard numbers between 250,000 and like more than 1.5 million viruses in the animal kingdom.
That's right. So there are many, many, many. And in fact, they're not strange beasts at all, if you think about it. I mean, if you were thinking about it in purely evolutionary terms, right, it's a profound way of conserving energy. You don't have to build your own mitochondria. You don't have to build anything. You just go inside. It's like, you just go inside someone else's house, sleep on their furniture, make copies of yourself, and out you go. And in the process, of course, you destroy the house, but that's a different story. But it's an extraordinarily efficient way. So in fact, I would twist the question around and ask the question, why aren't there more viruses? And we don't know the answer. Part of the answer is that we have lived as living beings. I'm not talking about humans. Humans are just a little blip in history.
Animals.
Say again?
Just animals.
Bacteria, plants, everything, living beings, have lived so long with viruses that in fact we've even learned to either have a symbiotic relationship with them or fight them. And so the question really is not, why aren't there so many viruses? The question is, why aren't there only viruses, right? Because viruses are extraordinarily efficient ways of reproducing their own kind.
So one of the fascinating aspects of recent pandemics, and we should also talk about past pandemics, is the zoonotic aspect, the fact that it's crossing the species barrier. And if you run through, there was obviously Spanish flu, bubonic plague, some of these catastrophes, but if you run through the most recent ones, Ebola, HIV, staggering HIV. 32 million people died from HIV. That's staggering. And also we should talk sociopolitically about why that pandemic took 40 years to resolve because of probably the populations that were targeted by it most conspicuously. MERS, right? Am I saying it right? Am I pronouncing it right?
Yeah.
Yeah, the Middle Eastern respiratory syndrome. SARS, which is COVID-1, right? And now here we are at basic, COVID-19 is also called SARS-CoV-2. And these are recent pandemics of this century, right? And yet, why is this one so different? The others have staggering statistics, upsetting statistics, but nothing like, with the exception of HIV, but it was also a 40-year pandemic. None of them with the statistics that we have now with COVID-19.
I told you what the particularly bad characteristics of this virus are, and we need to talk about them. So one of them is this, which actually shares with HIV, is the idea of the asymptomatic carrier. The asymptomatic carrier is a very, very particular beast that this virus has, and other viruses, some viruses have, not all viruses do. Ebola, for instance, really doesn't for the most part.
It doesn't. It's an almost 40 or 50% fatality rate.
That's right. So
even if it was 28,000 people, which is a much smaller number that contracted it in the most recent pandemic, it's still half of them die.
That's right.
Like, it's pretty devastating.
Well, it has a very high case fatality rate, which is a terrible thing, but it has a very low asymptomatic carrier rate. And so it allows, what happens with Ebola, just to contrast Ebola and SARS-CoV-2, is that Ebola you detect in patches. So you suddenly see a patch of people who get the virus. You can contain them, you can isolate them, you can treat them now with new antivirals and antibodies, and then you know that you've contained the pandemic. With SARS-CoV-2, the 2 or 3 problems, number one is this asymptomatic carrier problem. And you know, if you are a fan of the New York Times podcast, which...
The Daily?
The Daily, yes, thank you. There is a really, really interesting interview of a German female physician, whose name I'm blanking on, of course, who talks about the first case, and she begins to understand that this is a case of an asymptomatic or potentially pre-symptomatic patient who could infect others. You see, that is a big deal, because if you're asymptomatic and pre-symptomatic and you can infect others, that makes a huge difference, and it made a huge difference in the case of HIV. There were many and continue to be many people who are asymptomatic or pre-symptomatic, who will eventually develop the disease or may not develop the disease, but who can transmit the virus. And that is a particular Achilles heel that this virus exploits. The second one, of course, is the level of infectivity. So in the universe of infectivity, again, to remind ourselves, HIV is not actually a very infective virus. You need to do...
It's not airborne.
It's not airborne. You have to do quite a lot to get yourself infected by HIV. You have to have a relatively high viral load in the donor. You have to have a breakage of the blood barrier in some way or the other, which is complicated, as you know, and then you get an infection, right? Here you have a virus where you don't need to have any breakage of any barrier. This is airborne. And the infectivity rate, you can get much more easily infected. That combination is unique. There are other viruses that have that combination. So I'll give you a couple of examples. Measles is a virus where you have a very, very high infectivity rate, actually higher than SARS-CoV-2. You generally don't have pre-symptomatic patients, but there are some sort of quasi-pre-symptomatic patients, and measles spreads rapidly across populations. The difference between measles and this virus is that, generally speaking, aside from certain people, measles is not fatal.
Now, measles is an example of a successful vaccination program.
Yes.
Polio, smallpox, measles. First of all, I want to give you a forum to say something about anti-vaxxers. Because it's not that vaccines are benign. They are dangerous if they're new. But but the anti-vaxxers with polio, smallpox, measles, these are things that have been eradicated nearly globally because of vaccines. So I would love to hear your opinion on this.
Well, you know, where does one begin? Look, I think in this case, I mean, let's talk about specifics. I mean, anti-vaxxers are anti-vaxxers.
They're more common than you think.
Oh,
It's
I know.
just-
I know them very well. I mean, as I said, I mean, we were going to talk about at the end. I'm on the Governor's Commission for, it's a 15-member panel to reopen New York. And anti-vaxxers is a major concern. We have only 15 members. We meet every week, maybe every day. And we have a very detailed discussion about what's going to happen next and how to manage next steps. Anti-vaxxers are a major concern. Now, all I would say is that the vaccines that we're trying to accelerate for COVID, for SARS-CoV-2, are new kinds of vaccines.
Now, had we had a vaccine for SARS-CoV-1, which was nowhere near as infectious,
Yeah,
much lower numbers.
So, no,
Had
that
we developed a
vaccine program was halted.
It was halted because it stopped spreading. It was contained.
That's right. It was contained, and it was a different. It had actually a different kinetics as a virus. It was contained, and it really should have been continued.
Had it been developed, would we have a leg up with this one?
Yeah, we would certainly have a leg up with this virus. But anyway, that was contained, and the vaccine program.
That was just 2002, 2004.
That's right.
The
And
SARS
so that
outbreak.
was contained, and should have had, and same with MERS, should have had a continuous sort of low burn or maybe high burn program. I want to remind you, Janna, we were talking about this a little bit before. People often forget this. Vaccination is a mathematical game. And vaccines only work in what I call a Goldilocks spot. And it's very, very important to remember this in the public domain. By the Goldilocks spot, I mean the following. If an epidemic or a pandemic is contained, then the attack rate becomes so low. In other words, the number of people getting infected becomes so low that it becomes very hard to run a phase 3 trial of a vaccine. Does everyone understand that? Because if you only get 5 people infected in the vaccinated group and 3 people in the unvaccinated group, you will never reach statistical significance.
So it's good news and bad news.
It's good news and bad news.
Good news, it's not spreading very rapidly.
Great.
Bad news is that you can't test the vaccine.
That's right. So that's the easy part. The hard part is that if the attack rate is very high and many, many, many people get infected and you develop natural immunity, so-called herd immunity against the virus, once again you can't test the vaccine because everyone is already immunized. They've been immunized by getting an infection, sadly. So testing a vaccine isn't easy because you have to be in this, what I call, and I've written about it, you have to be in this Goldilocks spot where you have the attack rate exactly high enough that you can get a difference between people who are vaccinated and people who are given the placebo.
So putting aside, not putting them aside, but having already noted the incredibly successful examples of vaccinations like polio and smallpox and measles, my flu vaccination doesn't work very well, right? My flu vaccination's what, a little over 50% effective, and each year it has to be different. Isn't H1N1, in fact, swine flu, part of the flu vaccination now? Is that right? Because it was not contained?
I'm sorry, I'm going to get a little geeky.
I love geeky. You kidding? I mean, come on, people. We get so geeky here. This is it. This is cool nerdism. This is what we like.
Right. So, influenza. So what you might not know is I'm a virologist, really, by training.
You're a virologist, an internist, an oncologist,
They all
a
come
writer,
together.
a historian.
They all come together. So flu is a very particular virus. And if you want to know the details, you should know the details because you get the flu vaccine. So flu is an RNA virus, and it has a very, very bizarre structure, which is that it has 9 independent pieces of RNA, independent, and that's very important. So it's called a segmented genome. I can tell you this because I failed my virology test because I didn't know this.
It's a classic.
But now I know it. It has a segmented genome. Most viruses don't have segmented genomes. SARS-CoV-2 does not have a segmented genome, okay? So flu has a segmented genome, which is like saying it has 9 pairs of socks, or 9 socks in it. When a flu virus infects a pig in, let's say, China or India or Tennessee or wherever it might infect, and if it happens to be that 2 flus infect the same cell, they can do something called, they can mix and match. So H1N1 and H5N5 infect the same cell, and out pops H1N5. Because it's segmented, because they can mix and match like socks. The problem with that is that because they can mix and match like socks, H1N5 has never been seen by the human population. Right? Because it's a completely new recombinant influenza virus. And that's what makes some flus extraordinarily virulent, because no one has ever seen such a virus before.
No, why? Sorry.
SARS-CoV-2 does not have a segmented genome. It has a single genome, thankfully, and therefore has no capacity to make new recombinants of itself. That's point number 1. And sorry, I have to still continue to geek, but it's important. HIV, in contrast, HIV has a separate trick up its sleeve. HIV has what's called an error-prone replicase. I'm sorry about the words, I'll explain them in a second. What HIV does is that when it makes copies of itself, it makes errors in those copies. And so because it makes errors in those copies, it can mutate very quickly. And because it mutates very quickly, it can become resistant to medicines very quickly. SARS does not. It has a replicase, but it is not that error-prone. So in fact, this is not a bad virus. It's not like the flu.
So it's containable.
It's containable.
So it won't be like every year there's a new effort to find a new
Exactly. It's not like the
shot.
flu shot, because it has mutations. There have been mutations that have been detected, but so far they have been few and far in number. It's not like, so as I said, HIV has one trick up its sleeve. Influenza has a completely second trick up its sleeve. But SARS-CoV-2 has one incredible trick up its sleeve. And that's something to watch out for, and it's not been covered in the media, and you should know about it.
Which is?
It's part of it which is that we're still discovering its tricks. SARS-CoV-2's trick is that it doesn't cause a viremia for the most part. And viremia means that it doesn't go into the blood, it stays in the lungs. And for some reason, and I'll talk about the reasons, we've identified those reasons, it infects the lungs, and once it infects the lungs, the human immune response has 2 main wings. Wing 1 is the ancient wing of the human immune response, which is called...
I am curious about the human immune response. So when this thing attacks, I mean, that's an interesting part of the story, not to interrupt, but to dovetail, like, what is the human immune response, the natural response to this? The first person who ever contracted COVID-19, what happens to the body?
Yeah, so we need to know about that. And in fact, I'm writing a big piece on this. So if you're interested, you can read it. But there's a very, very good piece which was rather neglected. I told Janna, there's too much news in the world, too much unimportant nonsense news, and you need to read the news that's important and not nonsense. The important news is there's a very, very good article in the New York Times about the kinetics of the SARS-CoV-2 in humans. So very broadly speaking, very, very broadly speaking, there are three wings of the human immune response to the virus. Everyone with me so far? And I'm sorry if I'm boring the hell out of you. Okay.
I wouldn't let you do that.
The oldest wing of the human immune response, which I study actually, is called the innate response. It goes all the way back to sponges and ancient animals, Eutheria, every animal has it. And that is a response that does not detect any particular virus or any particular bacterium. It detects patterns. It detects damage. It detects danger. So for instance, among other things, it detects, I told you some viruses have RNA. The presence of foreign RNA in a cell, in particular cells, will kick off this response. And it's not specific to flu or SARS or this or that. And it's called the innate response because it is the opposite of the other one that I'll talk about.
This is already a fantastically complicated system that is evolved with the theory that it will be attacked.
That's right.
At some point, it needs to have an immune system.
So there is a war, and
I mean, even the concept of an immune system is miraculous.
That's right. We were talking about this piece that I just wrote in Cell, which talks about the word Kampf, which Ilya Mechkinov, who won the Nobel Prize.
The original vaccinators, right?
One of the original vaccinators, right, wrote about the word. He said that we are always in Kampf, always at war with another pathogen because everyone's at war. We are at war with each other because it's a war for survival. Anyway, the innate immune response, its job is to detect danger, patterns.
And to recognize self.
And to recognize self and to make sure that self is protected. And it has no specificity for a particular virus. It recognizes patterns of viruses, patterns made and bacteria, and sends out danger signals. And then kicks in the glamour. So it's the less glamorous cousin because we've studied it less. And then it kicks in the glamorous cousins. And the glamorous cousins are B cells and T cells. B cells make antibodies, and these antibodies are specific to the virus. T cells don't make antibodies. They go and detect cells that have been infected and kill those cells.
Yeah,
they're the glamour
killers.
queens of the immune response. Now, what we know about pathological SARS-CoV-2, and this is one trick up its sleeve, and it's an incredible trick, is that for some reason that we still don't fully understand, although we understand a little bit of it, SARS-CoV-2 paralyzes or diminishes or somehow screws with that innate human response, the innate immune response. Not the B and T cell response, which it does later, but it screws up the innate immune response. So what happens, we think now, is that for genetic reasons or for other reasons, people who don't mount a strong enough innate human response, the danger signal to SARS-CoV-2, basically allow the virus to replicate and replicate and replicate in cells when you get the infection. And then the B and T cells come in and say, my God, there is a crisis here. And then what happens as a result of that is the B and T cells come in and say, this factory is on fire. let's put this factory out by dousing it with everything we have. Put every anti-fire equipment that we have and blast it on the lungs. And the problem is that is pathological.
So is that's what's causing some of the body itself is causing some of the damage?
That's exactly right. And we just figured it out. We figured it out last week, basically. It's an extraordinary story, and that's one. There are other tricks that SARS has up its sleeve, but that is a main trick, which is that unlike other viruses, SARS-CoV-2, the trick that SARS-CoV-2 has up its sleeve is that it doesn't cause viremia, which is spread of virus in the blood, but rather it goes into the lungs, and in some patients, not in many patients, for reasons that we understand somewhat and we don't understand otherwise, SARS-CoV-2 blunts the innate human response, the ancient one, and then what happens as a result of that is that the B and T cells, which are the glamour queens or glamour kings of the human immune response, say, oh my God, the factory's on fire, put, anti-retardant on it, and that anti-retardant is essentially a bad thing because you get drowned in your own fluids.
So a friend did want me to ask you about certain genetic predispositions to being vulnerable to this particular disease, and one of them being quite obvious, things like blood type. And have you followed the arguments that O is protective and A is more vulnerable? What do you think about those theories? Do you believe that?
So I think there's some evidence for it, but those are very minor pieces of the story.
Mm-hmm. Because it does seem to have a pretty huge range in terms of how it affects people.
Those are very minor pieces of the story. Mm-hmm. The major pieces of the story, and they're coming out right now, has to do with genes that control the innate human response. There were two Dutch siblings, both young, both men, who were 27 and 21, very young, not twins, but siblings, who both had terrible COVID and died from COVID. And the question was, why on earth were these two Dutch siblings so badly affected? So they did genetic sequencing, and in both cases, and this is what's important, the genes that were problematic, or the genes that were mutated by chance, were genes that have to do with the innate human immune response. Not the B cell response, not the T cell response, but the innate human response. That's one extremely strong piece of evidence. The second piece of evidence, which is even stronger, and this is just one of the most amazing stories in science. It came out in Science magazine, done by John Casanova at the Rockefeller. Some people have, especially men, actually, disproportionately men, for reasons we don't understand, have an autoimmune disease which is really undiscovered. No one knew about it before because we've never looked before. They have an autoimmune disease that blunts their innate immune response. They have antibodies that they've made, autoantibodies, just like you have antibodies in multiple sclerosis or lupus, against factors of the innate immune response. And those people are the ones that are disproportionately affected by COVID. So here's the crazy thing about it. And the numbers are not small, 10, 12% of patients with severe COVID, and even up to 20% of patients with severe COVID have autoantibodies, autoimmune responses against innate immune responses. So what I'm trying to say is that 10 to 20% of COVID may be an autoimmune disease, which no one has ever thought about before. The reason I'm saying this is that maybe that's true for influenza. Maybe that's true. We haven't
Right.
looked
Are we going to...
so deeply at a
Right.
virus in this way. We've never, ever looked.
Well, even just the fact that we just listed a bunch of pandemics, or at least viral outbreaks from HIV, Ebola, MERS, SARS, and none have elicited this kind of reaction, societally, let alone medically. And even if HIV was first diagnosed in the U.S., I think in 1981, but it's suspected to have emerged in the early part of the 20th century, right? So this is really interesting that we don't, the diseases they're not brand new. This is called COVID-19 not because it was the 19th that was discovered, but because it was the year that they recognized it. But there are a lot of coronaviruses, a lot. And SARS-CoV-1 is another example of a coronavirus. And
most of them are harmless except for SARS.
So, but the interesting thing is, again, not to go back to this, but the crossing of the species barrier, where HIV, Ebola, MERS, so HIV is thought to have come from other primates, Ebola, probably other primates, MERS, camels, possibly, but there's a lot of reservoirs in pigs and bats. Avian flu, swine flu is probably also an avian flu. This back and forth between us and other species, and one of the things I want to ask about is that, 2020 has been a hell of a year. There are fires breaking out in California. Australia was devastated by fires in the past couple of years. And is there a relationship between our coexisting with other animals, climate change, and that is making these diseases either more readily transmissible or more aggressive, or that we're giving it back to the animals and the animals are coming back to us?
It's a very important question. The answer is there's no way to prove it, right? This is a thought experiment. But there are giant duck farms, pig farms, and giant reservoirs, ducks and pigs, where usually the flu originates. We know about the zoonotic infections that originate in the case of Ebola. I am concerned, deeply concerned, that SARS-CoV-2 may have been a BL3 leak.
What do you mean by that?
May have been a lab leak.
So that was going around that in Wuhan.
I know, for a while I thought it was just complete nonsense. But then I thought to myself, the main laboratory where coronaviruses are studied happens to be, coincidentally,
in Wuhan,
in the city where there's been a leak. Oh, no, I shouldn't say leak. Where there was an infection with coronavirus, and our racist presumptions are people are eating bats. But if you ask people in Wuhan, they say, we don't eat bats. Then there was pangolins for a while, and they were like, there were no pangolins. And so
right, because it was ascribed to have originated in a wet market.
That's right.
In Wuhan, where there was wildlife
and fair enough,
being eaten.
and I could be completely wrong, and but it's just a little weird that the main lab that in the entire world that studies coronaviruses and collects them from bat caves that are thousands of miles away, by the way, from Wuhan, happens to be the same city. And all the specimens have now been destroyed because we can't go backwards, etc. But it just sort of defies belief. And now I'm going to be imprisoned or something.
Well, I mean, there is this idea of the way things permute, and in some sense, like ecology and like climate change, some of it is incidental and some of it is intentional.
Well, I don't think it's intentional. I don't think that, I
For
don't
sure,
think
for sure. But I mean, some of it is like human manipulation.
No, I think I think we are living in closer and closer proximity to animals because of ecology, because of climate change, because of deforestation, because we are claiming land that we should not be claiming. And zoonotic viruses are emerging as...
Meaning crossing the species barrier.
Yeah, sorry, crossing the species barrier. And we have no immunity against them because we haven't experienced them.
Do you think it's an unusual run that in this fairly young century we've had so many outbreaks?
Oh, I don't think it's unusual. I think it's a consequence of climate change. I think it's a consequence of breaching barriers that we should.
I mean, if we look at the devastation of the Amazon, should we be surprised if new diseases
No, far from
break
it.
out?
No, far from it. In fact, I mean, one of the things that I think that, one of the lessons of SARS is in fact a climate change lesson. I think Joe Biden said it. He talked about it once. He should talk about it more, which is to say that the more we need to learn to live within limits. There are forests, there are animals in forests that have learned for centuries, evolved for centuries, millennia, to live with viruses. And just remind yourself, what's an advantage to a virus? A virus doesn't want to kill you, right? Evolutionary speaking, you're a mathematician.
Right, it burns out if it kills you.
That's right. It's a terrible thing it kills
you. If it needs you to replicate, then
That's
killing
right.
you isn't a very good idea.
That's right. So the viruses in humans that have been the most successful are viruses that have co-evolved with humans for millennia. So Epstein-Barr virus, right? So I would say in this audience, I would say about 80% of us carry Epstein-Barr virus. Do you know it? No. Do you communicate it to your partner, your sibling, whoever it might be? Yes. Cytomegalovirus, herpes simplex virus, all the herpes, chickenpox, right? These are extraordinarily successful viruses. They don't kill you, they replicate, and they move on. And the last thing, in fact, if you were a virus, is that a virus would want to kill you. The problem with the zoonotic viruses is that we're not adapted to them.
Right, so they just landed on you and didn't.
They land on you
and
they
to town.
And they go to town.
Right, and
as
you're dead.
And you're dead, and that's not what a virus does. A virus doesn't want to do that. It wants to maintain itself in you and move on to another person.
So I do want to ask about the realism of a vaccine. I mean, we've never had a vaccine turned around so quickly as we're trying to do. Of course, technologically and scientifically, we weren't as advanced. But the shortest turnaround, I believe, for a vaccine is about 4 years.
Yeah, that's for measles, yeah.
Measles. And
mumps, sorry.
Was it mumps?
Mumps, yeah.
Okay, it began with an M. And so here we are trying to devise a vaccine. And, vaccines are complicated. They use sometimes live viruses. I mean, you detail this in a really narrative and engaging way in your New Yorker articles about the first people who realized, if I put a little bit of this, if I grind up this scab, and I put it in an open wound in a child, I will actually inoculate them. I will kickstart their immune responses, and that's a pretty dangerous game.
That's right.
And it has to be done very cautiously and very correctly. So how do you feel about this flat-out race for a vaccine in such
we have
a
no choice.
rapid race?
We have no choice. I mean, we need to have a vaccine because there's no other public health strategy that we have aside from vaccinating people. Vaccines.
Unlike the flu, do you think it will be like a vaccine the way that polio was an incredibly effective vaccine, or do you think it will be like flu where it's a 50%?
Well, chances are it will be an
Inoculation.
effective vaccine. As I said, the tricks that SARS-CoV-2 has up its sleeve are not as bad as the tricks that HIV and flu have. I told you about the tricks, right? So HIV, flu has this, mixing socks trick, which is very tough because we don't know which socks
I
it's
didn't
mixed
realize
every.
that about HIV until
again?
we spoke. I didn't realize that about HIV until we spoke, that it has so many mutations and it's so
That's right.
flexible.
So the problem with HIV is that it's very mutable.
It's flexible and it changes from person to person. It can be
and it's mutable, and the dominant parts that you would direct the vaccine to can change. As far as we can tell, the dominant, and the only way we'll know is when we have a vaccine, right? It's an experimental problem. As far as we know, the binding domain the thing that SARS-CoV-2 uses to latch onto a cell seems to not have changed very much in humans. Now, when we've never applied a so-called pressure, which would be the vaccine,
to see if
it will start changing, and if we need what might be called a dual vaccine, in which we apply the pressure, but we also go from the side and apply a dual pressure, but we need a vaccine. So these are the newest kind of vaccines we've made. Usually, the way we've made vaccines in the past is by taking a virus and either killing it using formaldehyde and injecting that formaldehyde-killed virus to elicit a human immune response. So that's called a dead, killed virus vaccine. Or we've taken a virus and cultivated it in other cells, like egg cells or something, until it becomes a weakened version of the virus. So that's called a live attenuated virus vaccine, both of which are successful. All of these vaccines that are coming out are not that, except for the vaccine in China, which is a dead, killed virus vaccine. The vaccines that are coming out from the United States, the Pfizer, the Moderna, the AstraZeneca, et cetera, are vaccines in which we're taking either the virus and a piece of the DNA of the virus and putting it into another virus, a harmless virus. Those would be the adenoviral vaccines. That's the ChAd-Ox vaccines. So when you hear about the ChAd-Ox vaccine from Oxford, the AstraZeneca vaccine, ChAd-Ox stands for chimpanzee adeno vaccine. So ChAd-Ox vaccine, right? Oxford, chimpanzee adeno Oxford vaccine. So that's one set. The Moderna and the Pfizer vaccine don't even use any virus. They just use
DNA?
They just use RNA.
RNA, because it's an RNA virus.
And they inject you with the RNA, hoping to elicit an immune response.
So I'm conscious that I want to open it up to
a
questions,
million questions.
But one of the things I kind of want to know, and you and I have spoken about this before here in Pioneerics and other times, is where's CRISPR in all of this? Where's stem cells in all of this? So CRISPR, being the bacteria, has this innate vaccination card that it keeps using the DNA of the virus that has infected it. It puts the virus DNA back into its own DNA so it can send it to its offspring. So all of its offspring has this vaccination card and is inoculated against this virus. We don't have that, which is kind of amazing. It's unbelievable that bacteria do this.
CRISPR has played a major role. I spoke to Jennifer Doudna about it.
Who just won the Nobel Prize?
Who won the Nobel Prize
this year.
And is a close friend. CRISPR has been a useful tool to understand coronaviruses, but as far as vaccination strategies, it's not really been.
So we can't do that. We can't send a CRISPR mechanism into the human genome to edit our own genome
not
to
so
have
simply.
that vaccination card.
Not so simply, and we just haven't. There's no simple way. I mean, vaccination is an old idea. It's taking a scab from someone and putting it into someone else. CRISPR is a new tool that allows us to explore biology, but it's not a vaccination strategy per se. So I don't see CRISPR playing it plays a major role in understanding how the virus works. And that itself, as a secondary effect, can help us understand how vaccination works. But CRISPR itself, I don't think, is going to be the major tool for vaccination.
So I guess one of the things I want to ask you before we open it up to everybody else is this, some people have said things like, oh, we're going to have a coronavirus pandemic / plague once every 10 years. And is that something, even if we vaccinate against this coronavirus and we get past this and we all think, oh, we're free and our masks are off, are we just waiting a few more years before the next one?
Well, there are two questions there. One is a natural experiment that we'll have to go through, which is to say, is the coronavirus, this coronavirus going to mutate once we put a vaccination pressure on it? We don't know the answer to that. We'll find out, sadly. The second thing is that most coronaviruses, as we know, are not that bad. SARS, MERS, and SARS-CoV-2 aside.
I mean, they had higher fatality rates, but
Yeah,
they were
but they were
less
not
contagious.
That's right, they were less contagious, and they didn't have that pre-symptomatic, asymptomatic carrier problem. So if you ask me, will there be more plagues in the future? I would say yes, there will be more plagues in the future. We are deforesting, we are moving to zoonotic spaces, we are cultivating animals, we're eating meat way too much. We are, we should be readjusting to the realities in a larger scale. This is not going to happen tomorrow. But we're eating way too much meat. We are cultivating way too much. We are monocultivating way too much to be able, there's less genetic diversity. And if there's less genetic diversity, there's less there's less natural resistance to various viruses and bacteria, etc.
And we give it back to the animals, and
And
then
we
they
give it back to the animals, and they give it back to us.
and then we give it back to them.
Yeah, right, and
It goes
plus
back
we're
and forth.
feeding animals antibiotics. These antibiotics create resistance. I mean, we are in a bad cycle, and we need to break that cycle. And if we don't break that cycle, what happens as a result of that is that we get plagues, and when you say the plague, I mean massive.
I mean, this is 43 plus million people.
Well, it is 43 million
infected
people,
globally, at least.
25% unemployed in certain places.
Right.
You
So
know,
over
economies
1 million
halted.
deaths. Right.
I mean, this is not a joke.
This is no joke.
This is no joke. So
Yeah.
this is a global crisis.
So do you think that some of these social changes are going to be permanent? So for instance, if the CDC, if the CDC says in December there's
Janna,
a new
there's a difference
plague.
between think and hope. So I hope that this is a warning against monoculture. I hope this is a warning against, bad eating habits, bad consumption habits, bad deforestation habits, potentially climate change, all of which are linked. They're linked by...
Look at the countries that did the worst in containing it. They have basically despots in power, right? Like if you look at other places, they contained it much more efficiently, and there are similarly places that have a greater respect for their natural ecologies.
Well, I would prefer it if the way to contain a plague was not to have a despot. And
No, but they've failed at containing the plague, is what I'm saying. Like
but
Brazil,
China seems to have contained the plague very well.
Fair enough.
And so I would prefer it if we contain the plague.
Like New Zealand.
New Zealand is a good example.
It's a wonderful example.
It's a wonderful. Well, my daughters want to move there, so. And Germany, maybe, if there may be a second wave, I don't know. I have to say that whether despots or not, despots, not despots, these are just minor blips in the scenario, as it were. The really major blips in the scenario are we moving in the wrong direction kind of globally. Are we invading spaces? Are we doing monoculture? Are we doing, should we be doing things? Should we have a surveillance system, which is,
So
which is internationally funded, which is not a paralyzed, effete WHO? Forecasting, containing. Look, if you wind, everyone has a hindsight 2020. But first of all, when Trump calls it the China virus, he's lying, because most of the infections in the United States, in New York, in most of the Northeast, came from Europe. They didn't come from China. And they came from Italy and Spain, which then came from China, right? So the idea that we have a very global society, which is highly mobile, people are moving around, we need a surveillance system, like we have for the flu, that tracks and finds out whether things are moving and when to close borders down. I flew into LaGuardia from Croatia, which, by the way, is very safe because you can only enter Croatia with a negative PCR test. And I just walked, no, it was JFK, not LaGuardia. Walked off my flight, picked up my bags, and left. I could have flown in from Brazil, I could have flown in from God knows where, and spread virus everywhere. So we have the wealthiest country in the world, has one of the worst contact tracing systems. It has one of the worst vaccine distribution systems. We need to invest in all of this.
Before I get into the questions, can we just take a minute to thank Sid for joining us tonight in this very modest private event.
And look, Janna, New York is rising again, despite what Trump says.
Cheap gossip.
Yeah, cheap gossip. It's rising again. We will be back. We are coming back. We will be back. We will go to the opera again. We will wear masks. We have this is one of the safest cities in the world. Because we listened, we phased, and so let's keep that up. Don't defy rules. Don't congregate without masks. Be conscious if you are. Come on.
Yeah.
We are in a safe zone. Keep it that way. Okay? And we just we need to have the New York will and the survival instincts. We went through this in the 80s. We've gone through this in the 90s. We will go through this again in the 2020s. We will come back. Don't worry.
Yes, I love it. Woo, for New York. I'm going to consolidate some of these questions. One of the questions is, how useful would it be if we had daily or weekly individual testing? Even if less reliable, and I think that's almost a second question, because the
so we did
lack of reliability is a big
it's
thing.
An important question. For the governance panel, we did a simulation, and what's funny about it is that the simulation, Janna, you'll like this, because the simulation works out basically the same answer as a back-of-the-envelope calculation. So it depends on what your goals are, right? If your goal is to open a business, and if your goal is to open a restaurant, if your goal is to open a school, probably twice a week testing with a sensitivity and specificity in the 90% range is probably good enough.
But what about the fact that the test takes 3 days to come back?
So no, it does not. This is a complete misnomer. So tests can come back if you do it well. A good PCR test, which is highly sensitive, can come back in 24 hours. And there are 2 tests that are coming out, which will come back in 2 hours or to 3 hours. So you can sit in the playground, enjoy yourself, and once you're ready, you can go and attend your classes, et cetera, et cetera. So we are having a discussion with the governor to open up. And again, the amount of money that it would cost the city to do it this way, if you wanted to open up businesses, is actually kind of trivial. If you pool samples, so if you pool 10 people to a sample, and then you retest the person in that sample, if you retest that, I calculated the amount. It's on the order of $30 million a month. We are bleeding $30 million an
In
hour.
lost revenue, yeah.
So $30 million a month is trivial. We could do it. It would mean mobilizing the major universities.
Can we do it state by state? Can we, just as New York State, decide with Governor Cuomo and
we would need a pilot. We would need a pilot that would show that it's successful. Would there be leaks? Yes. Some people would get infected. Would that be worth it? Yes.
So here's another question. Is there any evidence that COVID-19 virus was engineered? I mean, you mentioned that it may have been leaked from a laboratory, which is not impossible, but engineered is the next level.
Yeah, I don't. So I've looked at the sequence. I've looked at the sequence carefully, many times over. I don't think it's engineered.
And what do you think about, because it looks a lot like SARS-CoV-1, even though it's my understanding, maybe you can correct this, that they don't, it's not a direct descendant of CoV-1, but they have a mutual descendant.
Yeah, they have a far
past
away
descendant.
past descendant. Yeah.
Do all coronaviruses have past, are they all related?
They're all part of a big family. They have, as I said, they're coronaviruses because they have this crown-like
protein structure around it.
protein lipid envelope, but they are not related. Some of them are quite harmless, actually.
So I'm having trouble reading your writing. I'm sorry, friend. There are questions about vulnerability. Why pre-existing conditions, for instance, things like autoimmune disease, cancerous histories, why do they make somebody quite so vulnerable to this particular disease?
We talked about this. So
it's part of the autoimmune.
Well, we talked about this. There are two levels of vulnerability to the virus. One is the people who don't seem to have any pre-existing conditions. But when you look at those people, many of them have this problem with innate immunity.
You would almost wonder if you had an autoimmune disease, if you'd be better off.
No one's really looked at that properly, but I suppose you could look at that. But
I mean,
anyway.
it has happened that there are diseases that target the young and the healthy precisely because their immune systems are so aggressive.
Right. And there are many such diseases, right?
Yeah.
So as I said, there are three levels. The second level is that if your innate immune system is intact, but you don't get proper B cells or T cells to the virus, then you can also be susceptible. So there are really 2 or 3 levels at which you can become susceptible to particularly susceptible to the virus.
So I think we've been going for a bit over an hour, and I want to be sensitive to people's ability to sit still with masks on. It's an added challenge. But I did want to ask, what do your optimistic moments sound like? I mean, what is that? I mean, clearly we're not going to have a vaccine incredibly quickly. We're not going to be sure about the efficacy of a vaccine. It may or may not. It may be like flu, 50%. It may be like something like
50%
polio.
is by the very good number, by the way.
It's a good number, but it's not what people imagine naively when they hear the word vaccine.
Yeah, I understand.
They hear cure. Right. And to say you're 50% protected is kind of a reality check. It means we're still wearing masks, we're still social distancing, that these changes may well be permanent. I mean, I can imagine if the CDC discovers a new coronavirus this December, 2020, unlike 2019, they're going to be telling everybody to put masks on right away. We're not going to have the same. So. And what do you think about the fact that they haven't?
Oh, gosh. I mean, I think if we had masked ourselves, relatively sealed our borders, done PCR testing and contact tracing, I'm sad to say we may have prevented 100,000 deaths.
I mean, that is huge, right? And the fact that we're looking at 1 million plus people who have died due to this disease, that's mitigated, right? It could have been significantly worse than that. And it also could have been significantly better than that.
No, I agree. I mean, I think, I think it points to a profound lack of leadership.
Is there anything you want to say in that regard, since we're airing this on Thursday before the election?
Vote.
So, just to pursue.
Well, so what is the optimistic scenario?
Yes,
just to
the
finish
optimistic
up?
scenario, exactly.
The optimistic scenario is that this is not a highly mutable virus, that we have a reasonable set, it won't be one, candidates in January or February or March of next year of vaccines, that these vaccines will produce 60, 70% protection. The virus will not mutate against the vaccine, and we will take 2 to 2.5 years to vaccinate everyone. And
So does that mean for 2 and 2.5 years,
globally,
we're doing this?
No, I think we will slowly relax in phases. I think we will remain masked. I think
So you better buy some of Andrea Lauer's fabulous masks for sale at the front there.
Yeah. I think we will remain masked for a little bit, and then we will slowly ease up those restrictions. I personally am in favor of vaccine passports. If you've been vaccinated and with an effective vaccine, I think you should be allowed to go into places where people who have not been vaccinated are not allowed to go into, because these are private businesses.
I mean, that's what people did with the smallpox, right? If you
So
had
listen,
been
I
exposed,
have to get a
you
flu
became
vaccine.
a carrier.
I'm a physician. If I don't get a flu vaccine, I can't come to work. So I don't see why a private business could make a decision, whatever it might be, to say, look, if you don't have a vaccine passport, you can't come into our store. Right. And maybe you can come into our store with a mask, but you'll be only allowed in on Fridays, when other people who are crazy like you are allowed in, and you can go infect each other.
It's kind of a variant on Casual Friday.
Exactly. TGIV.
Viral.
Thank God it's Virus Day.
Sid, I could speak to you all night, and I really hope you'll join us in the garden afterwards. And I just want to thank you so much for coming out. And this is such an important topic. It means so much to us.
Well, it's a very important topic. I think we should continue talking about it. I think, again, I'm optimistic. January, February, March. I think frontline healthcare workers will be front up. Teachers will be next. Firefighters, paramedics.
Where are mathematicians on this list?
I think
we're sort of like non-essential workers.
Astrophysicists, I think, are a little lower in the.
Yeah, that's what I was afraid of.
And exactly. Well, we'll get you one, Janna, and you'll be fine. But let's watch the data. I hope it's good. I can't tell you anyway. I don't know. We're looking every day, and we'll see what happens.
Well, thank you, Sid. Thank you for your writing. Thank you for your contribution to the state program to bring the state and the city back online. And thanks so much for joining us tonight.
Thank you. We're trying.
Thank you, Sid.